So with that, Charlie, can you give us an introduction?
Sure. As part of the Hayes Trinity Groundwater Conservation District's ongoing Waterwise speaker series, we're very fortunate to have the state climatologist John Nielsen-Gammon from Texas A&M here to give us a presentation on climate trends and weather trends in the hill country of Texas. Let's welcome him. Thank you very much, Mr. Nielsen-Gammon, for being here. You may proceed when you're ready.
All right, thank you. And yeah, thank you for the invitation. You may think you're lucky, but all you had to do is find my email address. It's it's my job to help the state of Texas and everybody make the best possible use of weather and climate information. So I'm happy to talk to you here. Yeah, so let me see. I do not have the ability to share my screen at the moment. You can either grant that to me or run the slides yourself. Either one will work.
Did you get that notification?
Philip, is that something that, okay.
Let's see. Yes. Let's see. Yeah, you gotta. Okay. Gotta change my permissions to make that possible. Oh, whoops. Nope. I need to be an administrator to do that. And I'm not an administrator, so I can't run my slides. Looks like it's all on you.
Okay, I'll just share my screen and just let me know when you want to go to the next slide.
All right, sounds good. So while that's coming up, thank you. The material I'm going to give you is mostly based on a couple of publications that are publicly available. Next slide. First one is a report that we came out a couple of years ago on extreme weather in Texas and historic and future trends in that. We're actually work right now on an update of that to get data through 2020 and actually through the first part of 2021, since there was apparently an extreme weather event in February that caught people's attention also. The second publication on the next slide is a paper that a whole bunch of us worked on. You probably recognize a lot of these names, which is basically focusing on the mismatch between what water stakeholders really want to know in order to be able to plan for future circumstances, and what information climate scientists typically provide or are able to provide. In other words, you have the questions, we don't have the answers. We have answers to a different set of questions, which may be helpful, and I'll explain how that works by showing you what we do have answers for and what I think that means for, say, groundwater management. Next slide shows. I want to start off by showing the trends of that have been observed for the major climate variables in the hill country region. And in fact, hill country being in the center of Texas, the trends observed in the hill country are pretty much the same as the average trends across the state of Texas. And if there are differences, probably you should trust the average trends over the state of Texas more than the local hill country trends, because trends, especially of extremes, rely a lot on the actual weather that happens. And as you'll see later, weather happens to affect different places differently at different times. So to get a robust estimate of trend, you want to average over as large an area as possible until you don't get a noisy picture anymore. Well, the time series of precipitation in Texas is kind of noisy. Unfortunately, Texas has a very variable climate. The average statewide rainfall between a wet year and a dry year can vary by a factor of 3. But in the midst of that, there is a statistically significant long-term trend in most of the state. As you can see on the right-hand panel, the trend has been pretty much zero in the Panhandle and other parts of West Texas. Some places have actually received a slightly less precipitation recently than they had, say, a century ago. But there's been an increase of 10 to 20% over most of the eastern half of the state of Texas, with Hays County basically sort of on the dividing line, trend increase of about 11% over the long term, with given the noise, translates into an actual trend of somewhere maybe between 5 and 15%. So rainfall has been increasing, but not uniformly across the state. Next slide shows temperature trends. And temperature trends have been increasing fairly uniformly over the past several decades anyhow. The plot on the left is showing Texas temperatures in the dark red, and beneath that are a couple of estimates of global temperatures. Texas temperatures are noisier than the global temperatures because Texas is smaller than the globe. If you're not averaging over a large area, you don't average out the noise. And I've even averaged over time, so these are 9-year averages that I plotted. It's still noisier than the individual years from the global average. But you can see, at least in general terms, the trend in Texas has been similar to the trend averaged over the rest of the globe. And since the 1970s or so, trend's actually been a bit larger than the rest of the globe. And specifically, it's about a 1/2 to 3/4 of a degree Fahrenheit per decade over that period of time. And you can find places in Texas where the observed trend is higher or smaller, but I don't think I would really trust those differences to be things to expect to continue. Basically, ongoing trend of a little more than a 1/2 degrees Fahrenheit is something that would be reasonable to expect. Next slide looks at temperature extremes. So that extreme event I alluded to in February featured cold temperature extremes. Of course, we get extremes on both ends in Texas. The way I've looked at trends for that is to look at the hottest temperature of the month in the summertime, averaging over the 4 warmest months, and the coldest temperature of the month in the wintertime, averaging over the 3 coldest months. So the left shows the summertime highs average across the state of Texas, and there's actually not much of a trend at all in the high temperature extremes. The spike that you see there is the year 2000, where we had several hot months, and September 2000 was record-setting in many areas. 2011, you might expect to be a big spike, and it is pretty warm during that period, but it was actually basically warm every day. It wasn't like there were a few super hot days. It was just steady, somewhat unbearable heat, shall we say. So not much trend in the summer extremes, even though you'd expect there to be one, since overall temperatures are going up. And my personal speculation for why we don't see a trend in the summer extremes is that people are using water more than they did 100 years ago. And a large portion of the water they use is being poured onto the ground. Urban irrigation, agricultural irrigation, and then in addition to that, people are storing a lot more water on the ground. Basically, all of the reservoirs in Texas were constructed over the past 75 years or so. And that means that instead of having land surface heating up, you've got water that doesn't heat up so rapidly. So I think changes in what's going on the land surface accounts for the fact that we haven't had a big increase in the super hot days. Now, over on the right there is the super cold days, and that has seen a big increase. A lot of the news coverage of the February event made the claim that climate change is making events like this worse, or making extreme events worse, and they even had explanations for why that might be happening. Well, climate change may be making one contributing factor to these events worse, but it's making most contributing factors better, and it's doing so rather dramatically. So what we see here is an upward trend in the extreme cold temperatures that's actually about twice as large as the trend in average temperatures. Temperatures have gone up by about a degree per decade for the coldest temperature of the month during the wintertime. And the reason for that is actually pretty straightforward. We get our cold air from Canada and from the Arctic. We don't grow it locally. And the Arctic has warmed faster than the rest of the globe. So when that cold air gets here, it's a lot warmer than it used to be 50 or 100 years ago. Okay, next slide looks at another aspect of extremes, in this case, precipitation extremes. Precipitation extremes matter for a lot of reasons. One of them that is potentially relevant is infiltration rates. If all the water runs off rather than getting down into the aquifer, then that's an issue. And if that partitioning between runoff and infiltration changes, then the same amount of rainfall could produce a different amount of recharge. So what we have seen across the state of Texas is, well, first off, we get heavy rain occasionally. The plot on the left actually shows the amount of rain you'd expect to see on the wettest day of a century based on historical data. And Hays County and the rest of the Balcones Escarpment shows up somewhat prominently as a green streak within a swath of blue, which means rainfall is more intense in this area, primarily because of the additional uplift of air as they are flowing south from south to north, carrying a whole lot of moisture. So you can trigger thunderstorms, you can provide extra impetus to the upward motion, and you get extra precipitation and extra intense precipitation. On the right is the trend in the one-day 100-year rainfall amount, expressed as a percentage change over the past several decades. And this is a noisy plot. You wouldn't expect any of these particular details to persist in the future, but you do see more greens than browns, which means that on the whole, there is an upward trend in extreme precipitation. And indeed, we have seen that across all of the South and Southeast United States, where you can find a few places where the historic trend is negative, but in most places it's positive. And on average, we're talking about roughly a 15% increase in the intensity of the heaviest rainfall. And in Texas, that's happened in the same place we've had an increase of rainfall overall. But at least there's a lot of evidence that the rate of increase of the extreme rainfall is going to be a bit higher than the rate of increase of the overall average rainfall. Now, the next slide shows one important implication of this, and that's with floodplains. I don't know how much you deal with floodplain issues, but it's certainly going to be it was in the news when we had Harvey. It's going to be in the news as some of the new floodplain analyses come online, because just recently in 2018, the federal government updated its assessment of the intensity of heavy rainfall. So a 100-year rainfall event has changed. In fact, the plot on the right shows how much has changed, how much it's increased over the previous analysis, with the green colors representing an increase and the browns a decrease. And you see there's a big swath across Austin, San Antonio to Del Rio, where there has been an increase in the estimated magnitude of extreme rainfall. That's not really because of climate change. Now, the reason there's more increased areas than decreased areas is climate change, just like on the last figure. But the reason you have that intense swath where it is is because the old analysis, which is those blue lines, basically didn't think it knew about the Balconi's escarpment and didn't recognize that there was local enhancement there. So largely what's happened is the analysis technique has kept up with what we already knew, that we're in Flood Alley in Central Texas. The increase in Southeast Texas is due to a whole bunch of recent heavy rainfall events like Harvey, but actually it's not recent rain in Austin doing it here. It's just getting more detail into the analysis and recognizing the propensity for extreme precipitation that's always been there. Okay, next slide. I want to shift gears and talk primarily about the future and how it is that we, as climate scientists, try to say something intelligent about what's going to happen in the future. There's basically three ways of scientifically valid ways of predicting the future. One is basic physical principles. If something's going on and you understand why it should be happening, that's useful. Science tries to do that. So that's an explanation of why, if temperatures are going up, we, at least at a first guess, would expect extreme cold, extreme warm temperatures to go up also. It's not the whole story, but certainly gets us a long way there if we can draw those physical connections. Next tool is the one I've been showing you, historical trends in different types of weather. Go back, please. If there's an ongoing trend, then maybe it'll continue. If you don't have a good physical understanding of why that trend should be caused by climate change, then maybe it's just due to randomness of the weather. So a trend by itself isn't much evidence, just like a physical understanding without any observations is not much evidence. And the third tool is climate model projections, which are the ones you hear about the most in the news. Climate models say such and such is going to happen. And that's a tricky business because you have to answer a whole bunch of questions to get a climate model projection. You have to say how much greenhouse gases are going to be in the atmosphere, what the concentration is going to be. You got to say what's the consequence of that for, say, global mean temperatures. You got to say, well, what does that mean for what's going to happen locally for things that we care about that might affect groundwater? And then the fourth question is, how do you actually bring that down into saying concretely what would happen under those circumstances to things like infiltration and recharge on one hand, and for that matter, usage of water on the other. And then to put it in perspective, you want to know whether those trends are going to be big or small compared to the sorts of variations you're already used to dealing with because of natural variability. So let's go ahead and take a look at a couple of those questions that are embedded in climate model projections. So next slide shows basically that the first step is not on climate scientists at all. It's on things like economists, social scientists, engineers, what have you, basically projecting how the world will evolve, how will society evolve, how rapidly will economic activity grow, how rapidly will energy use expand, how rapidly will people choose to switch to green energy as opposed to carbon intensive energy. Questions like that. And of course, if you can predict the future in that, you can make a whole lot of money. So there's no right answer that we know of presently. So the way we deal with that uncertainty is by having a whole bunch of scenarios or pathways that the world might evolve, ranging from, in the upper left, high fossil fuel intensity, rapid economic development, prosperity for lots of people, versus, say, in the lower left, a situation where society has actually chosen to forego some economic benefits in exchange for environmental benefits, and has done that in a very in a global way. So there's 5 scenarios that I come up with, and they all have different implications for how much greenhouse gases are going to get into the atmosphere over the next century. On the right, those colored lines show that. Obviously, if you've got large amounts of economic activity and you're still using lots of fossil fuels, you'll produce a lot of carbon dioxide and a lot of what's plotted here. Radiative forcing is the impact on the energy balance of the climate system. Bigger numbers, more of an impact. Each of those 5 colors actually represents what might happen if society doesn't choose to take further action to fight climate change. So they're sort of what we call baseline scenarios. So we can say, well, here's what happens if we don't do anything, or here are possible things that could happen. And then actions that can be taken are on top of that and bring each one of those curves down to some of those dotted black curves that you see below the colors. Those different possible societal evolutions matter a lot by the year 2100, but not so much more in the shorter term. Next slide shows the range of projections around the middle of the century is pretty narrow, and clearly we're going to have more of an impact on the climate system by then than we do now. We're probably actually not going to be at the lower end because we're not taking action fast enough to meet that trajectory. So probably a fairly narrow target where we're going to end up means basically warmer temperatures and so forth. Next slide. This is temperatures over the past 2,000 years, average over the globe, estimated by a variety of techniques. All of them give the same basic picture, which is to say temperatures have varied a bit. They were going down over the past millennium until recently. And then if you tack on the observations of global temperatures in the black, you find a fairly dramatic increase. So on a global scale, we're outside the range of natural variability. And the blue circle indicates what would be expected to occur in 2050, given those projections of greenhouse gases. Now, the size of that blue circle is larger than the previous circle because knowing what's going to happen to the atmospheric concentrations is not enough. You also need to know how sensitive the climate system is to those sorts of things. But no matter how sensitive the climate system is within the range of likely possibilities, we're still going to be outside the envelope globally of what has happened over the past several thousand years, or actually the past 120,000 years on a global basis, and will be warmer than we are presently. Now, the relationship between change and variability changes as you get down to a smaller scale. So on a county basis, the variability in temperature is a lot bigger, and we're certainly not presently seeing average annual temperatures which are well outside of the historical envelope. And we're not seeing rainfall amounts that are well outside the historical envelope either. But you can imagine and expect that the odds of things that are strongly related to temperature are shifting slowly but surely as temperatures are changing on a global basis. Next slide is a comparison of the climate model projections of historic temperature changes based on simulations and what's actually happened in Texas. So like over 1950 to 2018, the average rate of increase of observed temperatures was about 0.25 degrees Fahrenheit per decade. Climate models say that according to their simulations, it would have been like 0.3 degrees per decade. So pretty good match. A pretty good match over the most recent decades also. Observations actually show a bigger trend than the simulations. Simulations show that basically the trends that we're in the middle of right now ought to be similar to the trends that have happened over recent history. So models on the whole aren't doing a bad job with temperature, even though you can find models that don't look realistic, but the average is not too far off from what's been happening and what's expected to happen. Next slide shows the projected rainfall patterns. And Texas is sort of on the dividing line between increase and decrease. Now, this is the average of a whole bunch of individual model projections. And the best way to interpret this is to say roughly half of the models say rainfall will increase and half of them say rainfall will decrease, giving us an average near zero. There's much more of a consensus to the southwest. Rainfall is very likely to decrease in Mexico. To the north and northeast, precipitation is likely to increase, but we're sort of on the dividing line where it's not clear what will happen with the rainfall. Okay, so temperature is a big driver of drought and water availability, as is rainfall. And so the next slide shows something sort of farther down the line of the hydrologic cycle, which is soil moisture. We've got projections that are divided into West Texas and East Texas. Hays County's in the East Texas category. So let's go to the next slide and look at what's going on in East Texas according to the projections. So when you hear about projections, you'll hear about different amounts of detail. And usually you're getting just the very basic information. Climate models say such and such is going to happen. So I just want to unpack this slide for you and show what's in it and what the uncertainties are and how to interpret those sorts of aspects. So first off, three things are plotted. First one is the Palmer Drought Severity Index, which actually has problems in future projections. I don't trust it, so go ahead and ignore that one. The other two are soil moisture in the top 30 centimeters of soil and the full 2-meter layer. And both of those are sort of flat through the 1990s, and they trend downward fairly dramatically after that. So to interpret this, so first off, what is the scale? Well, the scale is unlabeled. It's numbers from -3 to 1. Those actually represent the magnitude of the change in the average compared to the typical magnitude of variability. So it's what we call normalized variations. So what this is saying basically is by the year 2100, soil moisture in 30 centimeters and 2 meters on average is going to be similar to what it is presently in a dry year. Not the driest year historically, but a relatively dry year. Okay, second thing to focus on is what are the models consistent in this? So the bars on the right actually show what's called the interquartile range. That's a mouthful. What the mouthful means is top of the bar and the bottom of the bar span the middle 50% of all the models that are going into this plot. So 25% of them, a quarter of the models are above the top, another quarter below the bottom, the rest of them are in the middle. So the green bar for the 30 centimeter soil moisture says that fully 1/4 of the models project that topsoil moisture will increase, and 3/4 of them say it'll decrease. And in fact, 1/4 of them say it'll decrease fairly dramatically. And they all say 2-meter soil moisture will probably decrease more than the topsoil moisture. Third thing to watch out for in this is what scenario is involved. As I showed you, there's lots of different possible futures. Some of them involve climate change action, some of them don't. The politics, of course, gets into that climate change action part, whether we should try to drive the emissions down and by how much and what the trade-offs are. But you all have responsibility on the adaptation side. You have to deal with whatever is actually going to happen to the climate, whatever choices get made by society. And as a result of that, what you would like to know is some sense of what will actually happen, as opposed to what would happen in the worst case scenario, perhaps the best case scenario, although those are kind of useful too. Well, this turns out to be, for future concentrations of greenhouse gases, the worst case scenario. Most of the projections you'll see, if there's just one projection, it's going to be the near worst case scenario. Climate scientists like to do that because the signal to noise is really useful that way. You're changing the climate system so much that most of the changes that get simulated are driven by those changes rather than just random variations in the climate. Then people who advocate action like to use the worst case scenarios to say, look how big things are going to be. Well, if you want a realistic projection of what's likely to happen, probably the best bet is to take one of these extreme case projections, which is RCP 8.5, and tone it down by maybe 30 to 50%. That'll get you something closer to the middle of the road of the full set of possibilities. And that's a reasonable expectation for planning. One might want to consider best cases and worst cases also. But in terms of expectation, general rule of thumb is take the worst case projections and tone them down by 30 to 50%. Okay, next slide. This is my next to last slide. And it's basically a listing of all the different things you actually would have to worry about to consider aquifer health and water supply, both on the demand side and the supply side. I focused on precipitation, temperature, and rainfall extremes. But there's also when the rain falls, which actually may change. The models seem to indicate, and the historic data indicates, if it goes up, it'll go up in the wintertime, and if it goes down in the summertime. Carbon dioxide is also having an effect on plants. They're more water efficient. So that affects the soil moisture balance and the balance between runoff and recharge also. Yeah, depending on whether you care more about runoff or recharge, you might be rooting for more intense rain or less intense rain. The more intense rain produces more runoff, and so that's good for surface water and bad for groundwater supplies in a sense. Okay, so I'll wrap up with the final slide, which is my contact information. These slides are available to you, and if you have questions that we don't have time to get to here or don't think of until later, please feel free to follow up with me. Like I said, it's my job to help everybody understand this stuff, and hopefully I can help you do that. So thanks.
Thank you, Dr. Nielsen-Gammon. That was great. I wonder, President Fultz, if we've got a minute or two for questions from the audience.
Yes, I think that would be a good use of everybody's time, and we certainly appreciate your presentation and having you here tonight. So let me ask first, board, if you've got specific questions regarding the presentation, and then we'll open the floor after that. Not seeing, okay, John, I see you unmuted. Did you have a question?
Yeah, real quick one. I'm just wondering what Dr. Nielsen-Gammon thinks would be the single more in his mind, or what he does to combat climate change on an individual basis, or what would you recommend that any one of us do? Anything come to mind?
Well, the individual action mainly makes you feel good about what you're doing. The actions that will actually turn out to matter will be the ones that get taken much more broadly. So you can be setting good examples, you can be influencing other people and plant the seeds of actions taken more broad case. Another approach is to influence the political process for toward whatever set of climate priorities you prefer, and making sure candidates are aware of your concerns of that, and influencing who's actually has the power to set policy at local, state, and national levels, which can then influence global agreements and policies.
Okay, thank you.
Linda Kay, I also saw you unmute. Do you have a question?
Yeah, I'm wondering if we could get just a real flash, brief picture of what actually you think is going to be, what is the best scientific expectation of what is going to happen in Hayes County in the next 10 years or so in
Right.
general.
Okay, so over a 10-year time frame, we don't have any basis for expecting systematic changes in rainfall. We do expect temperatures to continue creeping upward, which means greater surface water and soil moisture evaporative losses, as well as greater demand being driven by landscaping and that sort of thing. And of course, there's always the threat of extreme rainfall, but that's a statistical threat. One never knows where that will happen. So in terms of long-term trends, the temperature-driven effects on evapotranspiration are, and the consequences that has for both supply and demand would be the things that I think I would be most concerned about and most concerned about taking into account over the next 10 years.
All right, I have a quick question for you also. Had not thought about the impact or historical impact of land surface changes and how that may moderate temperature changes when you looked over the historical data set. I don't think anyone expects, though, that we'll continue to see additional reservoirs built in the state of Texas. So there may not be these large surface area changes in land use. So can you talk a little bit about, although, how much sway or how much impact has that had over your historical review of temperature change versus what you expect to see from this point forward into the future?
Yeah, very good question. The the long term, if you take the full data set, the trend is negative in the extreme heat. But if you look at more recent period, last few decades, the trend is positive. So that reflects the fact that large parts of the changes took place during the middle of this past century, and not so much change taking place recently. Yeah, I would expect that the future trends in extreme heat will basically keep up with the trends in average temperatures. So, so the expected value of extreme heat would be 0.5 degree Fahrenheit warmer every decade, which is not much, but it's increasing the odds of extreme heat. And in fact, for every 2 degrees of warming, the expected number of 100-degree days doubles. So that's probably a better sense of the sorts of impacts one gets with that sort of thing. There is some climate science that says it might actually be larger than that, because as we saw with 2011, once things really dry out, you get some pretty high temperatures possible. And we may be moving to a drier regime because of the higher temperatures, and that may make extreme temperatures more likely to occur. But we haven't seen that sort of trend present in the historical data yet. And it may not happen if the models are wrong.
Holly?
Linda, did you have a follow-up?
I have a question from kind of a groundwater perspective. So correct me if I'm not understanding this. As the temperature rises, soil moisture is going to decrease. Could we therefore anticipate or expect less recharge to the aquifer because of this?
Yes, that would be the expectation. Basically, the way to think of it is you got the soil layer, and if more water is going out from the top back into the atmosphere, there's less that's going down into the aquifer. Now, people on this call know, but some people on this call know much better than me how much of the recharge of the aquifer is coming through infiltration through the soil in that sort of slow fashion, or how much is getting through fairly rapid through the karst system. Through the karst system, the increased temperatures and decreased soil moisture really doesn't matter much at all. It's mainly that slower infiltration where that becomes important.
Thank you.
All right, I do want to open it up to the floor. If you are in the go-to meeting and you have a question, I am going to open that up now. I do see that Doug Weirman is unmuted. That's the best way to tell me, unless you happen to have your camera on and you can wave at me. But Doug, let's hear, do you have a question for Dr. Nielsen-Gammon?
Yes, I do. John, certainly appreciate the presentation. Great information and everything. I think we've been observing in Hill Country is borne out by what you say. My question's more on a policy level. You don't have to answer this question if you don't want to. But do you, your group, be getting requests from whether it's groundwater management areas or regional water planning groups on how some of these predictions and trends going forward are going to play into regional water planning in the state of Texas, whether it's on a groundwater management area basis or on maybe a regional water planning group?
I do, or have been invited on occasion to speak to regional water planning groups on climate change. Let's see. Most recently, along those lines, I spoke to North Texas Municipal Water District on what climate change said about how soon their new reservoir would fill up and that sort of thing, and broader issues. I'm also on the Technical Advisory Committee for Austin Water, as they're going through an update to their 100-year planning cycle. And I'm on that advisory committee with a couple of other climate scientists, so they've got, they're probably engaged with climate change more than just about any other entity in the state at this point regarding water planning.
All right, Doug, that answers your question. Looks like we don't have a follow-up. Do we have anybody else on the line that has a question? All right. Hearing none. I again want to say thank you to Dr. Nielsen-Gammon. You know, my hope is that we'll see you regularly. I think it's good for us to continue to be informed and have the best science in front of us as we look to fulfill our mission to protect and conserve the aquifer. So thank you again. I believe that we will have the opportunity, if that's okay with you, to publish your presentation on our website. And that'll be available then for anyone who couldn't be with us tonight, can at least look at your presentation, have your contact information, and of course we can refer back to it as needed if we have questions. So we appreciate your time. Feel free to remain with us or go about your evening. We're happy to have you, but I do know time is precious. So thank you.
Yeah, thank you very much. I spoke this morning with the PUC and ERCOT, who now, according to law, have to consult with my forecast before they make their regulations, and their first draft is due in 2 weeks. So I suddenly have a lot of work to do.
Mm-hmm.
Thanks a lot.
All right, thank you.